Finding patterns. So we're going to kind of jump back in history a little bit, 1869. Dmitry Mendeleev was a Russian scientist. He noticed that certain groups of elements had similar properties. There were many elements that were known in 1869, but there were many that were discovered later, and so he didn't have all of these elements. So what he did was he was trying to find an order or a pattern among these elements. I don't know exactly how he went about this, but I kind of imagine that he took like index cards and, you know, it's like, okay, here's fluorine and here's what I know about fluorine and here's carbon and its properties. And then he's like trying to arrange them and figure out how to make some order of this. What he found was if you list them in order of increasing mass, then those similar properties recurred in a periodic pattern. So periodic means to exhibit a repeating pattern. It happens periodically, every certain amount of time or every certain number of elements. So if we take the first 20 elements and list them in order of mass, 1, 2, 3, 4, 5, etc. The colors here are going to represent elements that have common properties. So hydrogen, fluorine, chlorine have some properties in common. Helium, neon, argon have properties in common. And so they repeat, a lot like the black and white keys on a keyboard, right? The black key that represents C sharp repeats every certain amount of keys on the keyboard. And so he found that this happened with the elements when he put them in order of increasing mass. And this was known as the periodic law. It didn't say why this happened, it just said, look, this happens. When elements are arranged in order of increasing mass, certain sets of properties recur periodically. That's why it's called a periodic table. It doesn't mean that it's a table sometimes, and other times it's not a table. It's referring to this periodic nature of the elements in their properties. There's a funny t-shirt that says, chemists do it periodically. Periodic table. So he organized the things into a table, and he made rows so that those elements with recurring properties ended up in the same column. So these lithium, sodium, potassium, those line up. They have similar properties. Beryllium, magnesium, calcium, helium, neon, argon. Hydrogen, kind of a weird guy. We'll talk about how hydrogen likes to be an exception to lots of things. There were some gaps in his table, empty spaces. And he predicted that elements would be discovered that would fill in those gaps. And he even predicted the properties of them. He predicted the existence of an element he called ecosilicon. Eca just means below. So he predicted an element would be found below silicon. And that was discovered in 1886 by a German chemist, Clemens Winkler. He named it germanium after his country. And this is how, in 1869, Dmitry Mendeleev completed the first periodic table. You guys play Tetris? You ever heard of Tetris? No. In the modern periodic table, the elements are listed in order of increasing atomic number, not atomic mass. Because there's a couple of places where the mass is out of order. Anybody spot one? 52 to 53.
Between it's cobalt and nickel.
Yeah, cobalt and nickel. Cobalt is 58.93, nickel is 58.69. You expect it to be higher. 52 and 53, tellurium and iodine, 127.6 and 126.9. Higher number, lower mass. And also, no, never mind. 90 and 91? Yep, thorium and, oh gosh. That's not palladium. PA. Can't remember what PA is. Patagonium. Just make something up that sounds official, right? There is Californium. Yeah. So our modern periodic table contains a lot more elements than Mendeleev's original table did because we've discovered more elements. This is just kind of a interesting periodic table. They're showing pictures of some of these elements. What we do want to look at here is, this is color-coded. And so the yellow section here, all of these elements are metals. And up here on the upper right of the periodic table, the green ones, all of those are nonmetals. And then we have these guys in between. You see this dark line here? That is the line dividing the metals and the nonmetals. And on our periodic table here, it's made with blue tape. Along that line, you have some elements that are called metalloids or semi-metals that are kind of between the metals and the nonmetals in their properties. A humanoid robot, is it human? No, but it kind of looks like a human, right? So C-3PO was a humanoid robot. He's got arms and legs and a head and a body. He has the shape of a human. He walks and talks, but he's not actually human. So a metalloid is like a metal, but it isn't actually a metal. It also has some properties in common with a semi-metal. And it kind of makes sense that between these in the periodic table, between the nonmetals and the metals, you'd find these things that are kind of in between in their properties. So we have those different classifications in the periodic table. I'm going to go over this part really fast because really it's just reading, and you can do this. So the metals are on the lower left, and they have common properties. They can be pounded into sheets. They're malleable. They can be drawn into wires. They're ductile. They conduct electricity. They're often shiny. Important chemically, they tend to lose electrons. The nonmetals, upper right, these vary more in their properties. Some of them are solids at room temperature, one's a liquid, and the rest of them are gases. And their physical properties vary a lot. They tend to be poor conductors of heat and electricity. They're not ductile, they're not malleable. They tend to gain electrons. So metals lose electrons, nonmetals gain electrons. And then the metalloids are in between. Sometimes they're called semiconductors because they do conduct electricity, but not nearly as well as the metals. And what makes them really useful is that you can control how conductive they are. We can also divide the periodic table into main group elements and transition elements. The main group elements are a lot more predictable, and the transition elements are kind of squirrely. Their properties aren't as predictable based on their position in the periodic table. So in the periodic table, the sections that stick up are the main group. And this sunken down portion in the middle, those are the transition elements. We also have vertical columns, horizontal rows. The columns are called family or groups. Some of these groups have names. They're all numbered as well. And then each horizontal row is called a period. Now this periodic table does have the numbers for the periods, and it's just row 1, row 2, row 3, going down. Within a group, this was based, our periodic table is based on Mendeleev's periodic table. And so in a group, the elements tend to have similar properties. Group 8A, there's different methods of numbering the periodic table groups. And this periodic table has both of them. We can number them straight across left to right, 1 through 18, or we can use what's on here with the Roman numerals and the A's and the B's. Personally, I like the numbers with A and B because I find them to be a lot more useful. So I will generally refer to those. Group 8A, that's that far right column, also called Group 18. Those are the noble gases. So they have a name. And they are a family. And just like people in a family have similar characteristics, elements in a family have similar properties. If you look at my children, you would notice that you can tell immediately that they all belong to the same family. It's like they were made with cookie cutters, but one came out a girl. And so they're just like, wow. Some people can't tell them apart. I think they look very different, but they all have similar characteristics. So far, all the boys like to play football, right? They have common characteristics, and yet they are not the same, exactly the same as each other. And so in the periodic table, in the same family or group, the elements are going to have similar characteristics, but they are not exactly the same. Noble gases, very unreactive, and they're all gases at room temperature. Group 1 are called the alkali metals. These named families, you need to know their names. The alkali metals, these are very reactive. You put a marble-sized piece of sodium into water, it explodes violently. They're very reactive. Group 2 is the alkaline earth metals. These are fairly reactive, but not like the alkali metals.
Okay, which one would be 2A then?
Group 2A, the other numbering is 2. So the letters help. If there's a letter on it, then it's one set of numbers, and if there's no letters, it's another number. The heat is melting my brain. Group 7A, these are called the halogens. These are very reactive nonmetals: chlorine, bromine, iodine, and fluorine. Metals tend to lose electrons. The main group metals tend to lose electrons to make a cation, and they're going to lose the same number of electrons as their group number. And the main group nonmetals gain electrons. They gain the same number, they gain electrons to make an anion with the same number of electrons as the nearest noble gas. It helps to look at the periodic table for this. Let's just jump to the periodic table. These are main group metals. This is group 1A. All of these metals stupid train. All of these metals are going to lose one electron. They're going to lose one negative charge, and that's going to cause them to have a +1 charge. The charge is written as a superscript on the right side of the symbol, and we always write the sign of the charge, plus or minus. If it's just 1, we don't write the 1. And what you'll see as we go through the semester is chemists seem to have a thing about the number 1. We don't like to write it unless we absolutely have to. So these are all +1, but we don't write the 1. The group 2A metals are going to form 2+ ions because they're going to lose 2 electrons. Here's aluminum, group 3A. It's going to form a 3+ ion. It's in group 3. It lost 3 electrons. And then these nonmetals in the main group. So let's think about fluorine, and let's look at the regular periodic table. How many protons does fluorine have? 9. So how many electrons does an atom of fluorine have? 9. The nearest noble gas is neon. How many electrons does neon have? 10. So fluorine is going to gain electrons so that it has 10 total. So if it has 9, it needs to gain 1 electron to have the same number of electrons as neon. So it's going to have a -1 charge. Oxygen has to gain 2 electrons, and nitrogen has to gain 3 electrons. So they're going to gain electrons so that they have the same number as the nearest noble gas. Okay? Let's go back to the word slides. So the group 1 metals tend to lose 1 electron, form +1. Group 2 loses 2, forms +2 ions. Halogens tend to gain 1 electron, and the oxygen family, which they're nameless, tends to form -2 ions. we'll learn a lot more about that later. At this point in the semester, what we need to be able to do is look at these main group metals and nonmetals and identify the charge that their ions have just by looking at the periodic table. So the cations, the metals, the charge is equal to the group number. For the main group elements, it's the charge is the group number minus 8. So oxygen is in group 6. 6 minus 8 is minus 2. This charge is minus 2. All of these guys form minus 2. So some students really like that group number minus 8. Other students do not. So here's a different way to remember these guys. So pretend we're playing a board game. And let's fill out this periodic table here. And I want to know what the charge on a nitrogen ion would be. So I find nitrogen, and I'm going to start here on my board game and count the number of spaces I have to move backwards in the negative direction. I need to go -1, -2, -3. This forms a -3 ion. If I want selenium, I start at the noble gas and I count backwards. -1, -2. It's going to have a -2 charge. So let's predict the charges of the monatomic ions formed by these main group elements. So nitrogen. Find it on the periodic table. Do you like group number -8 or count backwards? Count backwards, yeah, I think so too. 0, -1, -2, -3. So we predict that the charge would be -3. And we would write the symbol for that as N3-. Rubidium. Oh, question.
I always wondered, why does the sign come after the number?
Why does the sign come after? I don't know for sure. I ask a lot of questions like that to myself, and instead of actually going and looking them up, I just make up reasons. So I'll give you my made-up reason.
Okay.
I think it's to make it look different than math exponents.
Oh, yeah. Totally.
Works for me. So, if I had n-3, that could be the variable capital N raised to the -3 power, right? But when we write it like this, we wouldn't do that for an exponent. So that kind of says, no, this isn't a variable with an exponent. This is a symbol for an ion. So that's my reasoning behind that. Yes?
I always thought maybe it was a little different than oxidation state. So you might confuse an ion charge with oxidation state because oxidation state.
It does work to be different than oxidation states, but typically we don't write the element symbols with an oxidation state as a superscript. We do write them differently when we write them. We say the oxidation state is -2 and the charge is 2-. Yeah, and that does make them look different. How about rubidium? We have to find it on the periodic table first. There it is. Is it a metal or a nonmetal? It's a metal because it's on the left side of this stair-step line. If you have a hard time remembering which is which, find an element that you know. Iron. Is iron a metal? Yeah, it is. So that means everything on the left is a metal. So rubidium's a metal. Metals form positive ions. And they're going to form ions related to their group number. This is group 1A. So what's the charge? +1. So rubidium plus. And again, that's going to look different than math. In math with an exponent, you never write a positive sign. You just write the number. Here we're going to write the sign, and then chemists have this thing about the number 1. Any questions? Oh, yes.
For metals, it goes off of their group number, and for nonmetals, you start from the noble gas.
Yeah, so for main group metals, the charge will be equal to the group number 1, 2, or 3. And for the nonmetals, it'll be a negative charge, and there's different ways to remember that. Most students prefer to just count backwards from the noble gas, -1, -2, -3. Or you can think of the group number minus 8, or you can think of how many electrons does it need to gain so that it has the same number as the next noble gas. Whichever works for you. You're going to get the same result. Any other questions?